Today I'll be giving an introduction to proof theory and to one of proof theory's most prominent formalisms, the sequent calculus. Now, two questions that someone might ask themselves when they first dive into proof theory is, what is it and why is it useful? So in proof theory, what we do is we formalize proofs as objects in their own right, and then we can use mathematical techniques to investigate, analyze, and also prove facts about them. And it turns out that this offers a constructive and syntax-oriented approach to showing that logics possess certain properties. For example, one can make use of the proof system of a logic to be able to show that the logic is consistent, in other words, it doesn't derive any contradictions, also to write decision procedures for the logic and determine it decidable, as well as even to extract interpolants of formulae, given that your logic has the interpolation property. Now, what a proof system or a calculus is, we use these two terms interchangeably, is essentially a set of formulae we call axioms that we take to be true, together with inference rules. And what inference rules do is they take some number of formulae as input, as premises, and return a formula as output, which is called the conclusion. And by taking axioms and successively applying inference rules to them, we can construct what's called a proof, which derives the final conclusion of the proof is called a theorem. Now, two of the most prominent formalisms for constructing proofs are due to this guy on the right, Gentzen, who introduced both the natural deduction and sequent calculus frameworks. Both of these have had numerous applications in computer science, and the sequent calculus in particular has been quite fruitful for developing certain automated reasoning methods. For example, one can often make use of a logic's sequent calculus to provide a complexity optimal decision procedure for a logic. So that was just a quick overview of what proof theory is and how it's used. And before I go on to the main content of the talk, I'm going to quickly go over the structure of the talk. So what I'll introduce next very quickly is propositional logic, and I'm going to assume that everybody is familiar with propositional logic. And one of the reasons that I've decided to introduce proof theory in the context of propositional logic is, one, because it's well known, and second, because the formalization that I'm going to give is rather simple, meaning that this will give rise to a simpler sequent calculus and therefore simpler examples and proofs. After introducing propositional logic, I will then explain what sequents are, talk about how to build a calculus using sequents, as well as talk about different types of soundness and completeness, and then end by discussing what are called admissible or eliminable rules. These are rules where you're either free to add them to your system or take them away from your system. In the sense that the rules are essentially redundant. They can be used or they cannot be used. It does not affect what your system can derive, but it does change how your system can derive things. So these are two important concepts in proof theory that I will go into detail about near the end of the talk. Okay, so first on to propositional logic. In propositional logic, what we have are propositional atoms, a countable set of them, P, Q, and R, for example. And these essentially represent some sort of atomic fact, such as 1 + 1 = 2, or it's raining outside, for example. And our language of propositional logic is obtained by taking these propositional atoms, and you can introduce unary negation operators on them or binary implication operators. So these are the formulae for propositional logic, defined by this ENF grammar. I assume everybody's familiar with that. And I assume also that everybody's familiar with how to interpret propositional formulae. So an interpretation function is a function v which takes propositional atoms and assigns either a 0, meaning false to them, or a 1, which means true. And you can extend this interpretation to complex formulae by using the following recursive clauses. So an interpretation v maps a formula negation A to 1 or true if and only if A is mapped to 0, right? So not A is true if and only if A is false. And we have that A implies B is mapped to 1 by an interpretation if and only if A is false or B is true. I've also included the clauses for disjunction and conjunction. Even though these operators do not appear in our language, they will be relevant. These clauses will be relevant later on when we discuss the semantics of sequence as well as the soundness of our sequence systems. And I'm just going to define propositional logic to be the set of all validities. In other words, the set of all formulae which are true regardless of the interpretation of their propositional atoms. Now, a nice feature of propositional logic, and a desirable feature of logics more generally, is that it's finitely axiomatizable. What this means is that you can take a finite set of axioms and inference rules which generate all validities of the logic. And we oftentimes refer to these axiomatizations as Hilbert systems. Well, I want to point out a particular characteristic of this Hilbert system, and which is typically true of Hilbert systems more generally. And that's that there is sort of an asymmetry between the number of rules, inference rules, and the number of axioms. So for example, here we have 3 axioms and 1 inference rule. So typically in Hilbert systems, you have a large number of axioms and a small number of inference rules, and when we look at the sequent calculus, this relationship will be inverted. This is one of the reasons why the sequent calculus is better for constructing proofs in a particular way. But I will also explain in just a moment why the Hilbert system is not as efficient as the sequent calculus in constructing proofs, or at least in doing what's called automated reasoning, trying to discover proofs of formulae. So first, I will give an example proof of this Hilbert system, which is shown here in the middle of the slide. And afterward, I will explain the issues with provability in the Hilbert system. So let's look at how A implies A is derived using this Hilbert system. Well, according to line 1, we can take the axiom H1 and we can instantiate it with B with A implies A. The formula on line 2 is obtained by instantiating the B in H2 with A implies A and the C with A. And now, since the formula on line 1 is the antecedent of the formula or implication on line 2, this means that we can use modus ponens to derive the formula on line 3, which is the conclusion of that implication. Now I can take H1, I can instantiate B with A to obtain the formula on line 4. And this is the antecedent of the implication on line 3. So by using modus ponens, I can derive A implies A. Now, suppose that you give me a formula and you say you want me to determine if it is either valid or invalid. Well, one way of trying to answer this question would be to apply the inference rules of my calculus in reverse on the formula to try to construct a proof of it. If I can construct a proof of this formula, then I know it's valid because my system is sound and complete. It derives all and only the validities of propositional logic. And if I can't find a proof, or if a proof doesn't exist, then I know that the formula is invalid. Well, there are 2 issues with trying to use a Hilbert system in this way to do this backwards reasoning. So we might call forwards reasoning taking the axioms and applying inference rules to derive theorems, and backwards reasoning is taking a formula and reconstructing a proof of it, working your way towards the axioms. So what are the 2 issues with doing backwards reasoning in a Hilbert system? Well, the first has to do, well, both actually issues have to do with modus ponens. But the first thing is that if you give me a formula B and I want to try to build a proof of it, I have to apply modus ponens in reverse. So I have to go from the conclusion to the premises. Well, observe that in the premises of modus ponens, I have this formula A occurring. So this means that if I want to reason backwards, I have to guess what this formula A is that implies B. And it's not always clear how to do that. It could be the case that I end up searching for this formula A for an infinite amount of time, meaning this process of trying to construct a proof and determine if the formula is valid or invalid will never halt. And so I won't be able to determine within a finite amount of time if this formula is valid or not. So this is one issue with trying to construct proofs in a backwards fashion in a Hilbert system. The second issue with provability in Hilbert systems or doing proof search is that the size of the formulae can increase as you go from the conclusion to the premises. You can see this in modus ponens. The conclusion is B, and the right premise is of the form A implies B, which is a more complex formula. We can even see this in the example. The conclusion is A implies A, and the formula on line 2 is much bigger than the conclusion of the proof. So the issue with this, the fact that formulae can get more complex as we apply inference rules in reverse, is that it's not immediately clear if this procedure of constructing a proof by reasoning backwards is going to terminate. Now we'll see that in the sequent calculus, both of these issues are resolved. It will never be the case that we'll have to guess a formula when applying a rule in reverse, and also there will be a reduction in the size of formulae as we apply inference rules in reverse. So this is one of the reasons why the sequent calculus is in at least this regard superior to a Hilbert style system, because you can do backwards reasoning as well as forwards reasoning, which is useful for proving logics decidable and for automating reasoning using the sequence systems. Okay, so let's move on now to sequence, and afterwards I'll explain how to build a calculus using them. So a sequent is a formula of the form gamma turnstile delta, and gamma and delta are some sort of data structure that holds formulas. Namely, in our case, it will be formulae from the language of propositional logic. So gamma and delta can either be sets of formulae where duplicates of formulae do not matter and the order of formulae do not matter. They could be multisets where duplicates do matter, but the order of the formulae do not. And I've put an asterisk on the word multisets here because the sequence that we're going to use today can use multisets of formulae as opposed to sets or sequences. But also, depending on the logic you're constructing a sequent calculus for, depending on your application, you might, for example, have gamma and delta be sequences where the order and the duplication or duplicates of formulae does matter. So this is what you typically see, but I've included in ellipses down here at the bottom of the list to indicate that there are other possible data structures that can occur in sequence. You can have, for example, trees of formulae, or you can even have general graphs of formulae where you allow cycles, for example. But typically when we talk about Gentzen-style sequence systems, what we mean is that the antecedent is going to be either a set, multiset, or sequence of formulae. And again, today, our sequence will make use of multisets. So here is an example of a sequent. Gamma consists of these three formulae. It's the multiset that contains P implies Q, and P implies Q. Remember, duplicates matter in multisets. And delta is the multiset containing R and not P. Now, I want to introduce lastly on this slide some terminology. We oftentimes refer to gamma as the antecedent of the sequent. We refer to the turnstile as the sequent arrow. Also, sometimes the double long or single long sequent arrow is used to represent the sequent arrow. And we refer to delta as the succedent or sometimes as the consequent. And I use both of these terms interchangeably. Okay, let's now move on to how sequents are interpreted. So one nice feature of sequence systems is that usually you can extend the semantics of your logic to be used to interpret sequence as well. And here's a definition that explains how that is done. So we have that a sequent, gamma turnstile delta, is true is assigned 1 in the interpretation V if and only if the formula f of gamma turnstile delta is assigned 1 in V. Well, what is the formula of a sequent, or the corresponding formula? It's obtained by this equation shown in the middle of the slide. What you do is you take a conjunction of everything in gamma, you transform the turnstile into a implication, and you take a disjunction of everything in delta. I said earlier that gamma and delta represent multisets, but more particularly they represent finite multisets. So this happens to be a propositional formula. So we say that a sequent is true in an interpretation if and only if its corresponding formula is true in that interpretation as well. And that's how we extend the semantics from the propositional language to the language of the calculus, which is sequence. Now, this equivalently says, and I will use this sentence a lot, or phrase a lot, when discussing the semantics of sequence, that a sequent is true if and only if everything in the antecedent gamma is true, then something in the conclusion delta must be true. So if we look at the corresponding formula, that's essentially what it's telling us, is that a sequent is true when everything in the antecedent implies at least one thing in the consequent. Here's an example of transforming a sequent to its corresponding formula. It's obtained by transforming the commas on the left into conjunctions, by transforming the sequent arrow into an implication, and transforming the comma on the right into a disjunction. So we interpret the comma on the left conjunctively and the comma on the right disjunctively. So that is how we interpret sequence. And now let's move on to our sequent calculus for propositional logic. going to call our Sequent Calculus Lcp. CP stands for Classical Propositional Logic. And sequent calculi typically consist of three components. We have axioms. Axioms are nullary rules, meaning they don't have any premises, but what they have as their conclusion is an obviously valid sequent. In other words, a sequent which is true regardless of which interpretation is applied to it. And then we have what are called logical rules and structural rules. So first, let's look at axioms. So axioms are sometimes also called initial rules or initial sequence. And in our sequence system, typically you put the name of the rule on the right or on the left. The axiom rule is called AX. The conclusion is put underneath this inference line, and the premises will go above the inference line. Now, I said earlier that axioms are special in that they don't have any premises, so that's why there's nothing occurring above the inference line. Well, it's easy to see why the axiom rule generates valid sequence. Remember, according to what I said on the previous slide, a sequent is true if and only if everything in the antecedent implies something in the consequent. Well, if we assume that everything in the antecedent is true, then this A is true. So therefore something, namely A, is true in the consequent or succedent of the sequent. So this generates obviously true sequence. And now let's look at logical rules, and after that I'll explain structural rules. So what logical rules do is they take less complex formulae and they build more complex formulae by introducing logical connectives. In our case, that will be either negation or implication connective. Structural rules are different from logical rules in that what they do is manipulate the structure of sequence. So they might take two copies of a formula and compress it into a single copy. I'll explain these on the next slide. So let's first look at our logical rules. Logical rules typically come in pairs of left and right rules, which introduce more logically complex formulae on either the left or the right-hand side of the sequent. If we look at the negation left rule, for example, it says that if I derive a sequent where I have an A on the right, then I can put the A on the left so long as I introduce a negation. The negation right rule says that if I have an A in the antecedent, then I can put the not A on the right of the sequent. The implication left rule says if I have two sequents that are derivable where the only different characteristic of them is that one has an A in the conclusion or succedent of the sequent and one has a B in the antecedent, then I can introduce an A implies B into the antecedent of the sequent. And the implication right rule says that if I have an A in the antecedent and a B in the succedent, then I can introduce an A implies B into the succedent of the sequent. Now I want to point out how these rules are working in contrast to how modus ponens worked or derivability worked in the Hilbert system. So remember in the Hilbert system, if we tried to reason backwards, we had to guess a formula. Here, what's nice is that given a sequent or given a formula, we know that if we apply one of these rules in reverse, what the premise or premises are going to be. The premises are completely determined on the basis of the conclusion. You never have to guess anything. And the second thing is that we can see that the complexity of formulae decreases as we go from the conclusion to the premises. This is one of the reasons why the sequent calculus is useful for doing proof search or for reasoning backwards. So if we look at, for example, the negation right rule, we have a multi-set of formulae gamma and a multi-set of formulae delta, and these both occur in the premises as well. But this not A formula is now just an A when it occurs in the premise. So there's one less logical connective overall in the premise of this rule, showing that the complexity or size of formulae is overall decreasing as you go higher up in a derivation. Now it turns out that for propositional logic, these 5 rules are actually sound and complete for propositional logic, meaning that every validity of propositional logic is derivable using these rules, and anything derivable using these rules, if it's a formula, is a valid formula of propositional logic. So why do we need these additional structural rules? Well, which I will introduce on the next slide. Well, the reason why we have more rules is because oftentimes it's good to extend our calculus with additional rules so that we can prove certain facts and then show later that those rules are redundant or not needed to be able to derive all of the theorems that you want to be able to derive. And I will touch on this redundancy later. First, before I move on to the structural rules, I will discuss a bit of terminology that pops up a lot in the proof theory literature. So first of all is the notion of a principal formula. A principal formula is a formula which is explicitly mentioned in the conclusion of a rule. So in the axiom rule, it's this formula A. The axiom rule says that it doesn't care what multi-set you have on the left and the right, so long as they contain at least one formula in common, which in this case is A. So this formula is what makes this sequent an axiom. This is the principal formula. In the negation rules, it's the not A, and in the implication rules, it's the not, in the implication rules, it's the A implies B. We have auxiliary formulae. Auxiliary formulae are those which are explicitly mentioned in the premise or premises. So in the case of the negation rules, we can see that it's A, and in the case of the implication rules, it's the A and the B. And we also refer to principal or auxiliary formulae as active formulae more generally. In other words, an active formula is a formula which is either principal or auxiliary in an inference rule. And then we have what are called side formulae. These are the non-active formulae, or sometimes these are referred to as contexts. And these are just the formulae that sit to the side in the inference. They don't play any role whatsoever. Excuse me. Okay, now let's look at our structural rules. So here we have on the top of the slide two weakening rules, weakening left and weakening right. And what the weakening rules do is they let us add information. So weakening left says that we can add any arbitrary formula we want into the antecedent of a sequent, and weakening right says we can add any formula we want into the succedent of a sequent. If we look at weakening left, it's not too hard to see why this is a sound rule or what it's essentially saying. So what is the weakening left rule saying? Well, if we assume that the premise is true, then this means that something in delta is implied by everything in gamma. So if we look at the conclusion of weakening left, why is it true? Well, that thing which is in delta that was implied by everything being true in gamma is still implied because you have the gamma present. It doesn't matter that this A has been introduced. So this has to do with the fact that if you have one formula which is a consequence of a set of formulae or multi-set of formulae, then it will be a consequence of a larger set of formulae, of a superset of that set, because it still is implied by everything in that original set. So that's what weakening left is encoding, is essentially monotonicity of assumptions. Weakening right is saying something similar, but we're introducing a formula on the right. Then we have the two contraction rules, contraction left and contraction right. Both take two copies of a formula and compress it into a single copy. So if we look at the contraction left rule, remember that the comma on the left-hand side is interpreted conjunctively, or as a conjunction. Essentially, what this is saying is that A and A is equivalent to A. And that's true in classical reasoning. And the contraction right rule is saying something somewhat similar. Remember that the comma on the right-hand side is interpreted disjunctively, so this is saying that A or A is equivalent to A. And last we have the cut rule. Now, you'll notice that the cut rule is essentially a generalization of modus ponens. If we look at the premises, there's this formula A which gets cut out as you go from the premises to the conclusion. So if we were to try to apply the cut rule in reverse or bottom up, we would have to guess this cut formula A, just like we have to guess a formula while applying modus ponens in reverse. Now, I said earlier that the sequent calculus is good because we can oftentimes do backwards reasoning. We can construct proofs of formulae from the formulae themselves by applying inference rules in reverse. Well, the cut rule seems contrary to this claim. So why have I included it here? Well, oftentimes when we build our calculus, we introduce the cut rule, so that way we can prove that the calculus is complete. And I'm going to show in a few slides how to use the cut rule to show that our sequent calculus is complete. So it's temporarily helpful. You add it to your calculus, show the calculus is complete, and then after that, you do what's called cut elimination. And I'm not going to give a proof of this today because it's very complex and there's not enough time. But essentially what cut elimination does is it shows that anything derivable with cut in your proof system is derivable without it, which means that the cut rule, if you remove it from your system, this doesn't change what can be derived. Your calculus is still sound and complete relative to your logic. So that's why we include cut in the first place, but then afterwards show that it's redundant, that it's not needed to be able to prove all the theorems that you want to be able to prove. But it's an important rule to mention. Let's go through some terminology before I move on to giving an example of a proof or derivation in our calculus. So again, the principal formulae are those which are explicitly introduced in the conclusion. Cut does not have any principal formulae because a formula is just deleted from the premises to the conclusion. The auxiliary formulae, again, are those which are explicitly mentioned in the premises. The weakening rules do not have any auxiliary formulae. The cut rule has two, as do the contraction rules. The two copies of A are the principal formulae in the contraction rules. Again, active formulae are those which are either principal or auxiliary. Side formulae are those that sit to the side of the inference, aren't used in it whatsoever. And then the cut rule gets its auxiliary formulae are also referred to as cut formulae. Now I mentioned just a moment ago that oftentimes we want to show that the cut rule is redundant. And this is an important part of showing that your calculus is complete. So when we're proving this fact, we oftentimes want to differentiate between the auxiliary formulae which are used in cut and the auxiliary formulae of other rules. And this is why the cut formulae in the cut rule, or the auxiliary formulae in the cut rule, get a special name. So they're called cut formulae. Okay, let's move on to constructing a derivation, or also called a proof, in our system. And I'm going to use these 5 rules in order to build a proof of one of the axioms of the Hilbert system, namely the contraposition axiom, shown here. Now, we could take the axioms of our system and apply inference rules top-down to derive this axiom, or we could do backwards reasoning, which is what I've been emphasizing throughout the talk, that the sequent calculus is fairly good at. So what I'm going to do is show how to do backwards reasoning, or what's called proof search, taking this axiom and applying inference rules in reverse to extract a proof of it, or build a proof of it. So let's build a proof of this axiom. How do we start this proof search procedure? We take the axiom, we put it on the right of a sequent arrow. This can be seen here, highlighted in red. And now we start applying the inference rules in reverse on it. Well, there's only one main logical connective of this formula, which is this implication. And this implication occurs on the right-hand side of the sequent arrow. So we can apply the implication right rule. Now, if we apply the implication right rule bottom up, what happens is you take the antecedent of your implication, and you put it on the left-hand side of your sequent arrow, and you take the consequent of your implication, and you put it on the right-hand side of your sequent arrow. We now have this A implies B occurring on the right-hand side in this highlighted premise of implication right. And we can apply the implication right rule again. Again, according to the rule, the antecedent of the implication goes to the left of the sequent arrow, and the consequent of the implication goes to the right. Now the only complex formula that we have occurring in this sequent is this not B implies not A. So since it occurs on the left, we apply the implication left rule. The implication left rule says that in the left premise, we take the antecedent and we put it on the right. And in the right premise, we take the consequent of the implication and we put it on the left. Now we can apply our negation rules. Negation right says take not B and flip it over to the left-hand side, but remove the negation when you do so, as dictated by the rule. And negation left says essentially the opposite. Take a not A, or take the not A, which occurs on the left, and you're allowed to put it on the right so long as you get rid of the negation sign. And last, we can see that these top sequence are instances of the axiom rule. Why? Because there's a formula that occurs both on the left and the right-hand side. In the case of the left axiom instance, it's this B, which occurs on both sides. And in the case of the right axiom instance, it's this A that occurs on both sides. Okay, so that's how you do backwards reasoning in the sequent calculus. And as I mentioned earlier, these rules given here on the top of the slide actually do form a sound and complete calculus for propositional logic. But oftentimes it's useful, I'll say again, to have structural rules in our calculus initially. Or sometimes it's useful to know that structural rules are redundant, which is what I'm going to discuss after soundness and completeness in a few slides. Now, before I move on, I want to discuss an important metric in proof theory. There are a few different ways that we could try to define the size of proofs. We could, for example, define the size of a proof to be the number of sequents inside of the proof, or the number of inference rules in the proof, or maybe even the number of symbols. But one metric that we often use is called the height of a proof. Now, if we look at this example proof here, we can see that it's in the structure of a tree, where the conclusion of the proof, also called the end sequent, is the root of the tree, and all of the sequents which are given by the axiom rules are leaves of the tree. So if you look at the rules bottom up, what they do is they either have zero premises, such as the axiom rule, which then will be a leaf. They'll have a single premise, or they will branch, as in the case of the implication left rule. So this builds a tree-like structure going bottom up. Now, what the height is the height is obtained by finding the longest path of sequence in your proof, starting from the root going up to the leaves. So let's go through an example of how to calculate that here. We have two paths inside of our derivation. We have a left path that has 1, 2, 3, 4, 5 sequence on it. And we have a right path which has 1, 2, 3, 4, 5 sequence on it. So this would mean that the height of our proof is 5. So again, the height is obtained by finding the biggest number that corresponds to the biggest maximal path inside of your derivation. And I'll be using this metric later when I prove a property by induction about our calculus. Now let's go through different types of soundness and completeness. There is weak soundness, for example, which says that if a formula A is derivable in your calculus, then that formula is valid in your logic. Strong soundness says that if a sequent is derivable in your calculus, then that sequent is valid. So we can see that strong soundness implies weak soundness. All you need to do is instantiate this gamma with an empty set and instantiate the delta with A, and then you get weak soundness as a corollary of strong soundness. We also have a similar relationship regarding completeness. Weak completeness says that if a formula is valid, then it's derivable in your calculus, and strong completeness says that if you have a sequent being valid, then it is derivable in your calculus. Again, just like with soundness, strong completeness implies weak completeness. Now, in a nutshell, what this means is that if you use the adjective weak, you have soundness or completeness with respect to the logical language, and if you use the adjective strong, then you're talking about soundness and completeness relative to the language of your calculus, which is relative to the set of sequents that are being used. And I point out these different types of soundness and completeness because there are different methods for showing these. But today what I'm going to do is just show how to prove strong soundness and weak completeness. So let's go through the strong soundness proof for our sequent calculus. We want to show that if a sequent is derivable in our sequent calculus, then it's valid. And then we will know that by definition, our calculus is strongly sound. Well, how do we prove this? In essentially the same way that you would prove it for a Hilbert calculus. What you first do is you show that all the axioms of your system are valid, and then you show that all the rules of your system preserve validity. So, of course, if anything is derivable, it will be valid, because validity is inherited by whatever is derivable. So, how do we know that the axiom rule generates a valid sequence? Well, I mentioned this earlier, but I'll mention it again. We know that a sequent is true if and only if everything in the antecedent is true, then something in the consequent is true. Well, if we assume that everything in the antecedent is true here, then of course A is true, meaning that something, namely this A, is true in the consequent. So it's not possible to falsify this sequent, meaning that it's valid. Well, now let's show that the implication left rule is sound. In other words, it preserves validity. And the method of proof that I'm going to demonstrate to you here can be used for the other inference rules as well. For example, implication right, or the weakening left rule, for example. So if we want to show that this rule is sound, what do we want to show? We want to show, or we need to show, that's what NTS stands for, that if all of the premises are valid, then the conclusion is valid. Well, by contraposition, this is equivalent to saying that if the conclusion is not valid, then one of the premises is not valid. So it's just a matter of preference. You could prove the first claim, that validity is preserved downwards, or you could prove the second claim, which is equivalent, that invalidity is preserved upwards. It's just a matter of taste, but I like to prove that invalidity is preserved upwards. So that's the way that I'm going to prove that this rule is sound. So let's assume that the conclusion is invalid, meaning there's an interpretation V which makes it false, interprets it as 0. Well, remember that a sequent is defined to be equivalent to its formula interpretation or corresponding formula. So that means that the formula obtained by taking a conjunction of everything in the antecedent, which is gamma together with A implies B, by transforming the sequent arrow into an implication, and by taking a disjunction of everything in delta, is also false. So this corresponding formula is false by definition, since a sequent is defined to be equivalent to its corresponding formula. Well, now, also observe that this corresponding formula is an implication. That's its main connective. So if this implication is false, then that means, by definition, that the antecedent, everything in the antecedent is true, and everything in the consequent is false. Well, if everything in the antecedent is true, then this includes A implies B, so A implies B is true. And by the semantics of implication, if A implies B is true, then either A is false or B is true. Now what I'm going to do is make a case distinction. I'm going to show that if A is false, then the left premise of implication left is false. And I'm going to show that if B is true, then the right premise of implication left is true. And this will therefore show that under the assumption that the conclusion is invalid, that one of the premises is invalid. So let's assume first that A is false. Well, our left premise has a gamma on the left and an A together with a delta on the right. Well, by line 2, we know that everything in gamma is true, and we know that everything in delta is false, and by our assumption, we know that A is false. Well, this means that everything in gamma is true, and everything in the multiset A together with, or union with, delta is false. So it's not the case that everything in the antecedent being true implies the truth of something in the conclusion. Therefore, this sequent is false. Let's now look, or let's assume that B is true. In the case where B is true, we have that everything in gamma by the second line is true, and also B is true. So the union, which gives us the multiset gamma together with B, which is equal to the antecedent, everything in there is going to be true, and of course everything in delta is going to be false by the second line. So the right premise now has been falsified. So we've shown that under the assumption that the conclusion is valid, one of the premises must be invalid, which is the same thing as showing that validity of the premises implies the validity of the conclusion. So this rule is sound. And you can show the rest of the rules sound in this fashion. Well, now let's prove weak completeness. Now, typically when you show weak completeness, meaning showing that if a formula is valid, then it's derivable, one of the main methods is to harness the Hilbert system for your logic, which is known to be complete. And what you do is, to show weak completeness, you show that every derivation in your Hilbert system can be transformed into a derivation in your sequence system. So how do we show that this can be done? Well, derivations in Hilbert systems either have instances of axioms or applications of modus ponens. So first, what we want to show in our sequence system is that every instance of every axiom can be derived. So by using this small proof right here, we can derive the axiom in our Hilbert system, A implies B implies A. And also earlier I showed how to derive the contraposition axiom, which was not B implies not A, implies A implies B, when I gave the proof search example. And the third axiom of our Hilbert system, which I showed earlier, can also be derived in our calculus as well. So once we know that all of our axioms, all the axioms of the Hilbert system can be derived, the second thing we need to show is that all inference rules can be simulated. So in the case of our system, the only inference rule of our Hilbert system is modus ponens. And this little proof chunk down here shows that modus ponens can be simulated. If A is derivable and A implies B is derivable, then B is derivable. So what happens is, given a proof in your Hilbert system, you can transform it into a proof in your sequence system. So now, this is how completeness is obtained. We know that our Hilbert system is complete, meaning that every formula which is valid has a proof in our Hilbert system. And we know that every proof in our Hilbert system can be transformed into a proof in our sequent system. Therefore, everything which is valid has a proof in our sequence system. And that proves weak completeness. Now, before I move on, I want to point out one thing, which is that in showing that modus ponens can be simulated, we make use of the cut rule. So in showing the weak completeness of our sequent calculus, we make use of this rule, cut, which is not a good rule to have if you want to do backwards reasoning. If we look here, for example, we have our conclusion of cut being B, and the premises make use of this formula A. So with the cut rule, again, you have to try to guess formulae as you go from the conclusion of the premises. We do not want to have rules such as this in our system, but it can be shown that the cut rule is redundant. In other words, anything derivable with it is derivable without it. So as I was saying earlier, this is why cut is useful, or temporarily useful. It helps you show that modus ponens can be simulated, and then after that you show its redundancy, and then you have completeness of your system without the cut rule. That's the typical method. Well, let's move on to different types of redundancy now, namely admissibility and eliminability. So there are three common forms of rule redundancy that appear in proof theory. The first is the notion of an admissible rule. A rule is admissible if and only if anything derivable with it is derivable without it. So what that means is that if you want to, you can use the rule or not use the rule. You can throw it away from your system. We have a stronger notion of admissibility called height-preserving or HP admissibility, which says that anything which is derivable with a rule, or a rule is, say, HP admissible, if and only if anything derivable with the rule is derivable without the rule, and that derivation that doesn't use the rule has a height which is less than or equal to the height of the original derivation. What this means is that proving things without a particular rule in your system does not force the derivations to become larger. That's what HP admissibility means. And the last thing is eliminability. So we have that a rule is eliminable given that there's an algorithm which can be used to transform a proof with the rule into a proof without the rule. And of course, this implies admissibility as well. Because if you have an algorithm that transforms a proof using the rule into a proof without the rule, then this means that anything derivable with the rule is derivable without the rule. Now, before I move on to explaining each of these in a bit more detail and giving examples of them, I want to explain what the benefits of rule redundancy are. So, again, if a rule is redundant, what this means is that either you're free to either use it or not use it in your system. Your system doesn't necessarily need it. So what this means is that by either adding it to your system or taking it away from your system, you can change how things are derived, what kinds of proofs you have, but you do not change what is derived. And depending on your application, it can be useful to change how you derive things. So that covers the first one. The second benefit, which I'm going to mention today, is with respect to trading rules. So this is something that I discussed in my PhD thesis. It turns out to be the case that sometimes you can have a calculus, and if you add a redundant rule to it, say an admissible rule, then another rule in the calculus becomes admissible once that rule is added. So if you want to, you can now take that rule away from your system. So what this does is it allows you to trade rules. Again, this allows you to change how things are derived, but not what is derived. It allows you to transform your calculus so that maybe it proves things in a fashion which is better for a particular application. Also, another benefit of redundancy is parsimony, in particular rule minimization. If you want to minimize the number of rules that your calculus has, it's good to know which rules are redundant and which ones are necessary for completeness. And also proof search. I mentioned a few times earlier that the cut rule is actually redundant in our calculus, and also that the cut rule is not useful for proof search since you have to guess the cut formula in the premises when you apply it in reverse. Therefore, showing that the cut rule is redundant helps you obtain a system which is better for doing backwards reasoning, or proof search as we call it. Okay, so let's move on now to looking at these three different forms of redundancy more concretely with examples. So again, a rule is admissible if and only if anything derivable with the rule is derivable without the rule. And it turns out that our weakening and contraction rules are admissible. In particular, we're going to look at an example of weakening left being admissible with respect to this derivation. In other words, here on the left-hand side of the slide, we have a derivation which makes use of the weakening left rule, and we can see that we can obtain a derivation without weakening left, which derives the same conclusion. So this shows that, at least with respect to this derivation, the weakening left rule is admissible, that this conclusion which is derivable with it is derivable without it. And again, we can show this in all generality, that given any derivation, if it makes use of the weakening left rule, there exists a derivation which does not make use of the weakening left rule. And I'm actually going to prove that in a couple of slides. So that is an example of admissibility. Before I move on, though, why is it the case that we can go from this first derivation to the second derivation? Well, if we observe the conclusion of weakening left, we can see that there's a formula, namely A, which occurs on both the left and the right-hand side of the sequent, meaning that the conclusion of weakening left is an instance of the axiom rule. So we can squash these two inferences into a single inference, into namely just the application of the axiom rule. Let's move on now to Hp-admissibility, or height-preserving admissibility. A rule is height-preserving admissible if and only if anything derivable with the rule is derivable without the rule with a derivation of the same height or less. That's what it means to be Hp-admissible. And if we look at the example from the previous slide, we can see that the derivation which used weakening left, which is Hp-admissible in this case, has a height of 4, and the derivation without the rule has a height of 3. Now, it turns out to be the case that our weakening and contraction rules are not just admissible, but height-preserving admissible. However, this is not always true of admissible rules. For example, the cut rule is admissible as well, and that's something I will discuss in a future lecture. But when you remove cut from derivations, it tends to increase the size of derivations. But luckily, with respect to weakening left, weakening right, contraction left, and contraction right, this is not the case. It's always the case that derivations stay the same size or decrease in size. And I'll prove that in just a moment. Okay, last we have that a rule is eliminable if and only if there's an algorithm which transforms any proof with the rule into a proof without the rule. Again, we'll consider an example with weakening left, and here's an example algorithm. What it says is that given a derivation, such as this derivation shown on the left, we want to find a top instance of the rule. And if we can do that, then what we do next is we permute it up. So we swap the rule that we want to show is eliminable, in this case weakening left rule, with the rule that occurs above it. So here, the rule that occurs above weakening left is this implication right rule, which introduces A implies A on the right, and then weakening left introduces a B on the left. So now if we permute the weakening left rule with the implication right rule, instead we apply weakening left first, and then we apply implication right second, meaning we first weaken in with this formula B, And then we introduce the A implies A into the conclusion of the sequent. And now we just repeat this process going back to step 1 with the newly obtained derivation. Well, as I said a couple slides ago, if we apply the weakening left rule to an axiom instance, those two formulae, A, in this case A and A, which occur on the left and the right-hand side of the sequent arrow, both occur on the left and the right-hand side of the sequent arrow in the conclusion of the weakening rule, and therefore you can squash these two. So permuting a weakening left rule above an axiom is the same as having it be absorbed into the axiom. And so this is the derivation that we obtain in the end. So this shows that the weakening left rule, at least in this case, is eliminable, but it turns out to be eliminable in general. So here are 4 theorems which are true of our Sequent Calculus Lcp. We know that the weakening left, weakening right, contraction left, and contraction right rules are all height-preserving admissible. And also something which is nice is that the method of proof that we use to show that these rules are Hp-admissible, you can extract an algorithm from that proof which shows how to, given a derivation which uses one of these rules, how to delete these rules from that derivation. And essentially it's that algorithm that I showed on the last slide. So this, again, is one of the benefits of proof theory. I said at the beginning of the talk that proof theory offers a constructive approach. And that's what's nice is that oftentimes when we prove that our calculi have certain properties or proofs have certain properties, we can extract algorithms from our proofs. So not only do we get the Hp-admissibility of these rules, but also as a corollary, the eliminability of all of these rules. So I'm going to prove the first theorem, that weakening left is Hp-admissible. And then after that, we will be done. So I'm going to prove that the weakening left rule is height-preserving admissible based on the, by induction on the height of the derivation above weakening left. So the smallest derivation you can have is of height 1 and is just an axiom instance. So the derivation height above weakening left is just this instance of the axiom rule. And as I said before, applying a weakening rule to an axiom rule gives an instance of the axiom rule. So you can squash these two together. And observe that the derivation that is obtained is of height 1, whereas the input derivation was of height 2. So this is height preserving. The derivation does not grow bigger. Now let's look at the inductive step. And usually when we prove things by induction on the height of a derivation in proof theory, in the induction step or inductive step, we make a case distinction. The case distinction is made on what is the last rule applied. So in this case, what is the last rule applied before weakening left? Well, we're going to consider the case where the last rule applied before weakening left in the given derivation is the negation left rule. And one can show that what I'm about to show you holds in all the rest of the cases, for example, in the implication right case. So we assume that we're given a derivation, and we're doing a case analysis, but I'm just showing again this negation left case. We're assuming we have a derivation where the last rule applied before weakening left is this not left rule, negation left rule. Now, by assumption, we have a derivation, and this triangle up here is just representing that there's some derivation, which is ending with these 3 sequents, or 2 inferences. This, the height of the derivation, ending with this sequent highlighted in red, the conclusion of the negation left rule, is assumed to be of height n plus 1. And what this means is that the premise of negation left has a derivation which is of height n, because it's 1 higher up in the derivation. This means that we can make use of the inductive hypothesis on this sequent, because by the inductive hypothesis, we know that any derivation which has a height of n has weakening as an admissible rule for it. So this means that if we want to, we can weaken in this b by using the induction hypothesis. So now we obtain the sequent obtained in red. We have a proof of the sequent in red, which is of height n. And we can apply the negation left rule to move the a over to the left-hand side and introduce a negation. And observe that the height of this derivation is of height n plus 1, whereas the given derivation was of height n plus 2, because the sequent in red had a derivation of height n, so its conclusion had a height of n plus 1, so the conclusion of weakening left was of height n plus 2. So this shows that weakening left is height-preserving admissible. And observe that we can extract the algorithm that I mentioned earlier when talking about eliminability from this style of proof. So when we invoke the induction hypothesis, what we are saying is that we can apply the weakening rule first and the negation left rule second. So what we're saying is that we can swap applications of rules. And that's why this algorithm that I introduced earlier, where you can swap weakening left above any rule in a given derivation, can be used to eliminate weakening left from any given derivation. It also demonstrates that this method is a constructive method. And the same thing can be said for the weakening right rule, the contraction left rule, and the contraction right rule. All of them are HP admissible, and all of them can be swapped with rules until they're deleted at the axioms in a given derivation. So now just a quick summary. The reason why we are making use of sequent calculi as opposed to Hilbert systems, or at least one of the reasons, is to try to obtain analytic provability. So essentially, a proof system is analytic whenever you can derive something, all of the information that occurs in the proof is somehow contained in the conclusion of the proof. And what this means equivalently is that given a formula, you can extract a proof of the formula from the formula using the rules in your system. And we saw that that was the case with the sequent calculus. Now, sequents are objects of the form gamma, turnstile, delta, where gamma and delta can be either sets, multi-sets, or sequences of logical formulae, and sometimes they could be richer structures as well. Sequent calculi typically consist of three components: axioms, logical rules, and structural rules. We had two different kinds of soundness and completeness, weak and strong. Weak means that it's sound and complete with respect to the logical language, and strong soundness and completeness means that the system is sound and complete relative to the language of the calculus, or sequence. And we had three forms of redundancy: admissibility, Hp-admissibility, and eliminability. And what I'm going to discuss in future talks is the elimination of cut. In other words, providing an algorithm which shows that cut can be deleted from any given derivation, therefore implying its admissibility or redundancy. Also, another thing which I'll discuss is invertible rules. And these are rules where not only does the validity of the premises of a rule imply the validity of the conclusion, but the opposite holds true. The validity of the conclusion implies the validity of the premises. This is useful, for example, in proof search. So I'll give a future lecture on how to take a proof system and use it to obtain a decision procedure for a logic. And then also, I'll talk about different types of extensions or restrictions of the sequent calculus. So there are, for example, logical extensions. So we can look at first-order logic or modal logic. We can look at logical restrictions, such as intuitionistic logic or even linear logic. And then also, I'll give a lecture talking about structural extensions, meaning extensions of sequence using much more complicated data structures, like, for example, labeled sequent calculi or nested sequent calculi, which are used in modal logics and temporal logics, as well as description logics. So that covers the lecture for today, and thank you very much for listening.